And in particular, the word unitary will be involved here to a great extent. So we will consider a unitary structure on our vector space V, which I remind you is finite dimensional complex vector space. What is a unitary structure? It's going to be a pairing that I write like this. And I will warn you, in physics, there's a slightly different notation. You will see things like this, and you will see things like this. And you have to ask always what these symbols mean. But we will keep, you know, in physics you've seen things like this. But we will have the most simple symbol of all. So, it took me a while to get used to the so-called bracket symbolism. So, this is a pairing from the vector space to itself to complex numbers. And this pairing will satisfy a number of very important properties. So I'm going to list the properties and talk about this. Okay? So the first property is bilinearity. So complex linearity in the second argument. I warn you, this is the opposite of what mathematics usually does. There's a good reason for it to be this way. I like this. And second of all, complex antilinear in the first argument.
Isn't it the other way around?
I just said that. This is, who said it's the other way around? Yeah, you. So, you're right, it's the other way around in mathematics, but it's this way in physics, and it's much better this way. Remember my axiom, always try to use a physics notation. This is much better. I think mathematicians will change over time. I see them doing it. One reason is to think, it's just a psychological reason, but to think for V in V, this thing here, yes, you fix V in the first argument, fix it. I hand it to you. You fix it. And then you let this thing run. This is a mapping from B to C is linear. You really want that argument for the linear variable to be on the right side somehow, right? But mathematicians crazily didn't do this. Physicists, of course, do it this way. It's correct. Okay. So that is the first thing. Now, this mapping, dedicated to a friend who asked me about this, let me call this FV. This is a functional defined by V, right? If I put W in here, I get an answer. FV of W is VW. Right, it's a linear functional defined by V. Okay? So observe the way to think about this, and this is a very important thing. Observe this, i.e. V goes to the functional FV is an antilinear map from V to V star. Right? You take a vector, you put it in this first argument, yes, hold it fixed, and let this vector run, you get a function. Right? This association from a vector to a function is antilinear. So it is an antilinear map from V to V star. Keep these things in mind, they really appear.
I think you should write what linearity and antilinearity mean, because I don't think people know.
Okay.
Yeah, but they do know, I mean, at least the physics.
Well,
You know?
how long does it take to know? I mean,
They know, I mean, we did linear, right?
What does it mean, though? okay, linear means C linear, so it's additive with respect to V plus W, and yes. And when you multiply V times I, it comes out front as I, right? F of I times V is I times F of V. That means linearity with respect to the complex numbers. Okay? So it means if you put a complex number Z times V, F of Z times V is Z times F of V. That's linearity. Antilinearity means F of Z times V is Z bar times F of V. That means if you have Z equal to I, it comes out front as minus I. Okay? And this is the way to think in quantum mechanics in something called time reversal. So these things really, really occur. It's not just some silly thing. Okay. So it's very important to analyze what you really have. You have an antilinear mapping from here to here. Okay. Now the kernel of this mapping, I'm going to call it V perp. The reason I'm calling it V perp, it's all the things, the V's, such that this thing is zero, so that means that this thing is really the zero functional. That means it's identically zero. This means that V is perpendicular to all of V. You hate me. Why not? Right? Why not? You can have a vector which is perpendicular to everything. Right? It's possible. I didn't say anything about this thing here. It can be degenerate. It can be zero math. Right? But it could be, you could have some, what we call degeneracy. So V perp is called, so this is a set, this is a set of, let me write it here, correct? This is a set of V such that V is perpendicular to V, right? And we call this the degeneracy of this form. Okay, you could have it. You look mystified by this. Either that or your eyes are bad.
Oh, teacher, I can read it. I'm sorry.
Yeah, I thought your eyes were bad.
Yeah. So I can
Okay.
say.
You're looking at all the vectors which are perpendicular to the whole space. And if you check, that means those are the vectors, when you put them here in this thing here, well, it's perpendicular to the whole space, so you get the zero map. So that's the kernel of this map, everything that goes to zero. Okay. Okay.
Do you find this in real life?
Hmm?
Do you find this in real life?
Yes. I'm going to give you something in real life in a minute. That's a very good question. You find this in real life? My wife would ask this question also. Yeah, she's always asking me this. What are you doing there? You find this in life? Okay, but I'll talk about it in a minute, okay? So, now, assumption, let's call it, here's the first properties, let's say these are the first two properties. Second property I'm going to worry about is this map is non-degenerate. So you win, in my real life, at this stage, there will be no degeneracy. I will assume that nothing is degenerate to the whole space, is perpendicular to the whole space. Okay. We're going to assume this. Now, let me talk about real life. So, really, let's take an example of V equals C2, okay, standard basis. Okay. And we identify this with pairs of vectors. So Z and W are pairs of vectors. And so I'm going to have to tell you sort of the standard form that I like here. Convincing, I hope. What did I say? The first argument is antilinear. And the second argument is linear.
Who is it for?
Hmm?
Who is it for?
I'm not sure what you're confused about. So Z and W are pairs in C2.
Z1, Z2.
So let me, I think I know what you're confused about. Z is Z1, Z2.
Oh, okay.
And that's what you were confused about, right? Okay. Right. So, I mean, anybody can write this thing down. Yeah? So, that's antilinear in the first variable, and linear in the second variable. It's okay, right? And you can check, it's non-degenerate. Nothing has norms zero. So, well, that's good. But when you take this form and restrict it this form to subspaces, restrict this form to a state. Remember, a state is a one-dimensional subspace, L. Let's see what we get. E.g., I'm going to take, let me see if I, oh, well.
I do not agree with you.
Hmm?
I do not agree with you.
What do you don't agree?
No. If you take Z1 and Z2 points on the same circle, then that is your.
Hmm?
If you take Z as a pair of 2 points that are
Oh.
on a circle.
Thank you. Now you agree? Sorry, thank you. You have to watch it. Sometimes I just write complete, I don't know what I write. Thank you. Okay? Yeah, but it's exactly your point. If you restrict to a line, what happens if I restrict to the line, do I really want to do this? So I want to restrict to the line L equals, say, I hope this is right, Z, restricted to the diagonal. So let me just write it. L is this line. Okay? What do I get?
It's a circle should be.
Hmm?
Is it then should be
Let's try. Let's put it in. This is the line. So the line generated by this point. So this means, well, what does it mean? So if we take a point in this line, this point in this line is of the form ZZ, and therefore the inner product of V And W is just, well, the scalar part of lambda ZZ, well, lambda ZZ, okay, that's one point, and another point will be WW, right? Hmm?
You have W everywhere.
Okay. Well, I don't care. Z, okay, lambda, lambda, and mu, mu. You happy with that? Classical education. What is that? There's an answer on this line. So let's take V and W in this line and compute. You're better computing than I am. I hope it's zero, right? Okay. Okay? Is zero. Okay. So you see, this form restricted to this line is completely degenerate. Completely degenerate. It's a zero form. Okay? And we have learned that restricting the geometry to various states and seeing what happens in the various states is of fundamental importance. This state is an isotropic state. Isotropic means it's just completely zero when you restrict it. So it happens. Here's the state here. If I took it and moved it over there a little bit, just slightly, yeah, you can see what happens to the form. You restrict it, it's no longer, it's non-degenerate. Yeah, you can see what happens. Okay, so degenerate forms occur naturally by restriction. You can imagine, I could make a higher dimensional example. I would restrict to some subspace. It would be only partially degenerate. Right, I can make an example. Okay? So I think that's what happens in real life. You see in real life, my example, I put a minus sign in my example. If I had left the sign positive, this would not have happened. Right? So a third condition is norm of V equals 0. So what is the norm of V? VV equals 0 implies that V equals 0. Okay. This is something you like. Now I call this the norm. It could be negative, right? Why not? I mean, VV could be negative definite, but we will always assume, we will always adjust the sign so that norm is positive for V negative. Okay, three conditions. The linearity conditions, the non-degeneracy condition, which forces this mapping to be an isomorphism. So V to V star is an isomorphism. It's an antilinear isomorphism. And the final condition, we require that when you restrict, nothing bad happens. That's equivalent to this condition. Yeah.
I have a question. Does the first property imply that it's like the inner product of A and B is the inner product of B and A conjugated?
Okay, so no, and I think I've forgotten this condition. I don't. You see that implies that?
No, I don't see it.
No, I think you're pointing out in a nice way that I've forgotten that condition.
Because then you don't have to suppose this. I mean, you don't have to adjust the sign if you suppose that.
Is that really right? It's automatically positive?
Yeah.
Why?
Because VV is not real.
No,
It's real. not-
it's real.
It's real.
So this is so we're having a nice discussion here. We want the norm to be real, right? And his condition, which I forgot to write, is the reality condition, right? It forces reality, exactly that condition. Isn't it exactly the same? The norm being real is exactly the same as your condition, as this condition, right? It's close anyway. So thank you for reminding me. Let's see here. So maybe 4. Oh, this is a reality condition. Well, I'm sorry, there's a huge number of conditions, but I think they're all very natural, right?
So 4 implies 1, so 1 is the one that is not necessary.
4 implies 1?
Yes.
Well, no. 4 implies half of 1.
No, it implies both.
No, I need some linearity. 4 doesn't have any linearity in it. So if I assume it's linear in one thing, 4 implies it's antilinear in the other.
Oh, okay, yes.
Okay. Okay, I'm dedicated to, you're an observant guy, so I write it here. 4 implies 1/2 of 1. I don't believe in efficient writing down things. I believe in maybe even too much, right? Just to make sure we have the concepts here. Norm needs to be real, that's his condition, that's good. Linearity, antilinearity, non-degenerate, what else? That's it, right? Okay, this is called, for me, this is a unitary structure on V. This is a unitary structure on V. Let me just mention, structures of the type, in the example above, as you see, some norms are negative and some norms are positive. This is a mixed signature structure. These occur in life, as you know. Right? So you have the light cone of positive vectors, and then you have the stuff on the outside and so on. You always want to assume a non-degeneracy. This is unique. So you may not have unitary, but if you don't have the positive definite assumption, the word here might be pseudo-unitary. Okay, this word pseudo implies implicitly that the signature of the form is not necessarily positive. Some norms negative, some norms positive. Okay, so we'll deal with this. So fine, unitary frames. So a unitary frame is, as usual, a basis. And this basis should be unitary, so it should obey the geometry of this frame. So a basis of unit vectors. And these vectors are perpendicular to each other. So you picture these vectors in the usual way, with angles and so on. You might have, this is a picture over the real numbers, but at least in terms of this unitary form, of this form, they are perpendicular. Okay. So you can imagine. Okay. So, the symmetry group. Well, it's the group of transformations, I will call it U, of the vector space with respect to this form. Now, you should learn in mathematics to write everything down at first, maybe. So I wrote everything down there. You need the vector space and you need the form to discuss this matter. But after a while, discard this horrible notation, okay? Because it's too much. It gets on your nerves and you can't, even though we can write text very fast, I would not recommend it. I will call this thing for our lecture K. Now, I will explain sometime during the course of this lecture why the letter K is appropriate. is that. In other words, K is the set of transformations which preserve the linear structure and furthermore preserve the geometric structure for all x and y. V. So these are the unitary isomorphisms of the vector space. Well, I wrote you this thing in GL because it needs to be an isomorphism. But it's pretty clear that if it preserves the metric, then it is an isomorphism, because if something got killed here, you would get 0 on one side here that's not 0 on the other. So you don't really need that. So this is a group. This is the group of symmetries. Another remark is that I hope you know this from your considerations, is enough. So you do not need to prove that it's, if you have a transformation, you want to check if it's unitary, matrix, for example. You only need to check it on the norm. Yeah, you don't need to check it on the full inner product. Okay, do you know this fact?
Yeah.
Okay. So you can learn, you can check that. Okay. Well, if U is a unitary frame, oh, I should mention that there exist unitary frames. Right? Maybe they don't exist. Okay, let's start. This physics has a much better thing, so I'm going to ask you guys. So, the first vector in this frame has to have a length 1, right? Now, all these vectors have to have length 1, right? In the frame. Okay. I give you the first vector. Okay. So U1 with norm U1 given, U1, say is given by God. Now this guy's from Nepal, so he's in the mountain in Nepal meditating. Are you a Sherpa guide? No. So he's from Nepal in these incredibly beautiful mountains. And are you from Kathmandu? I think, no, you're from, we talked about this before.
Yeah.
From some more beautiful town than Kathmandu.
Yeah.
Higher, above Kathmandu. So he goes to some highly non-trivial mountain and is meditating, and God comes and gives him this vector with length 1. And God says to you, listen, you're a physicist. You've got to find these other vectors. Right? And he says, okay, no problem. I take the orthogonal complement of this first line. Right? I mean, this vector defines a line. God knows about that line. Yeah? And you say, I take the orthogonal complement. Right? And you say, just look in the orthogonal complement and I find something perpendicular to it. Then I have two, well, I make it norm 1. Then I have the two vectors. God says, what are you going to do with those two vectors? I say, I make another subspace of dimension 2, and I take the orthogonal complement of that, and I get a third vector. Right? And so on. You tell God, I don't need to do it and so on, because you know what and so on means. It's an algorithm that you learn in life. Just keep doing it. Otherwise you go to hell. Okay. Right? That's an argument. This argument uses something. You should look, this argument's trivial, right? You just take something like 1, look at the orthogonal complement. So, you should look what it uses. It uses the fact that the orthogonal complement of the line is disjoint from the line. Right? Because it could be you have a vector of length, well, okay, you see what I'm saying. It's very important to understand that orthogonal complements are disjoint. And if this thing is not positive definite, you may not have that. Okay, this is not a problem here. So go to the orthogonal complement and take 2 here, etc. Okay, so that's how you make it from. Okay. So note, if U is a unitary transformation, and this is a unitary frame, then a new frame is built by U of, I apply U to the first vector, U to the second vector, and so on. I push around the unitary frame with the unitary group. This is also a unitary frame. You know that already for linear transformations. If you take a basis and push the basis with a linear transformation, it's still a basis. Here, you take a basis and you push it with a unitary transformation, it remains unitary. I mean, it's completely obvious, right? Because this thing has length 1, therefore this has length 1. These two are orthogonal, therefore these two are orthogonal. This preserves the geometry. Okay? There's something even better. Suppose V1 through Vn is another unitary frame. You have 2 unitary frames, and then you do something incredible. You define U to map Ui to Vi. So you have this frame, U1, U2, U3, and so on. It could be a frame like this and a frame like this, 3 dimensions if you like. And then I just move this thing over here with the unitary transformation. The first vector goes the first vector here, and so on. With the transformation. I didn't say, oh, it's too fast. With some transformation, I define it like that. Okay? Guess what? U is automatically unitary, right? This transformation is unitary. Okay? If you don't believe me, check it. You just have to check that it's automatically unitary. So you define it like this, and you check that U is actually unitary. So this means that you can get all, start with a background frame, background basis, you get all other unitary bases by pushing around the unitary group. In big boy language it says the unitary group acts freely and transitively on the unitary frames. It acts transitively because it pushes everything around, and freely it means that nothing is stabilized, only the identities. So, that's that. Now I would like to speak then about at the matrix level. Remember always when you go to the matrix level, when you do things like this, we were talking at lunch with Professor Penkoff, who's an algebraist, do algebra slowly and write carefully what's going on with the diagram if you can. Right? If you can, just try to write with the diagram. Have courage, because algebra is so strong it will lead you with formal algebraic calculations to the end. So you have a unitary transformation here, and you have a frame transformation here, and we have the matrix of the unitary transformation here, and we have the same frame here. Somebody asked in the first lecture, should you really use the same frame on both sides? Well, come on, I mean, you're fixing the structure on the vector space. You can't just fiddle around and change frames all the time to get the right answer. You understand what I'm saying? If you're allowed to use, you get any answer you want. So you must use the frame map here on both sides. Okay, and the question is, this frame map, so this frame map of, say, the unitary basis, background basis, is, say, U1 through, which is unitary. This frame map maps this onto the standard basis this is the standard basis, standard frame in Cn. And this is a unitary frame. So this says that, well, this transports the unitary structure to the unitary structure here. So it says that mu, the matrix, preserves the standard unitary structure. You can do that, you can check what I'm saying here. On Cn. The standard unitary, these are coordinates. In some sense, what well, not only in some sense, in a very real sense, this sends a vector to its coordinate, right? And the unitary structure, the standard unitary structure, standard on Cn is just this structure. I wrote it up there with a minus sign. Okay? This is the standard structure on Cn. Now what does this structure mean? It means this thing is Z1 bar, W1 bar plus Z2 bar, W2 bar plus and so on, Zn bar, Wn bar. Okay. And now what's the norm of this structure? Just to convince you I'm playing the right ballgame. The norm of the structure, as you see, you take V, W equal to Z. This is absolute Z1 squared plus absolute Zn squared. This is the standard norm on Cn. Okay, you just check. You write down here what happens, you write down here what happens, you write that this comes to that, and you check what the induced structure is down here, and it's just simply that. And the statement is that this matrix, as an operator on vectors, on column vectors, preserves that structure. Check. Well, let's see what that means. See what that means. In mathematics, you just need to be courageous with your scrap paper and realize you can throw it away if it's wrong. So all that means, if this, let's make it short, so the matrix of this transformation, let's just call this U. Okay? And the statement is that if you take Z, it's a column vector times the matrix U, and W column vector, and you apply the standard inner product to it, it doesn't change. Right? That's what it means. It doesn't change. Right? Let's write it down. Great. That says that this thing, bar transpose, times this thing, doesn't change. you talk about calculations, you do this, right? You bar transpose, having fun, and so on. Right? This says that Z bar transpose, U bar transpose, U, W is the same thing as ZW. Right? Okay? Okay? This says that this vector here, this says, let me just give you a proof for fun. Z bar transpose, maybe, is this okay? You don't mind if I write this? Is that the same? Am I allowed to bring that over like that? I think so. Right? Look what that says. It says that this vector here is perpendicular to every vector. Right? This vector here is perpendicular to every vector. This is, right? What is that vector then? Zero. It says that this operator is the zero operator. It says that U bar transpose equals the identity. That's great. I've computed the inverse of the operator of the matrix. U inverse is equal to U bar transpose. Now, some language I like very much. The physics notation here is U dagger. The reasons for that, which I will explain, but it's just good shorthand. It helps us. It's called U dagger. The tet command is tet, D-A-G-G-A-R. So I will use this thing. Okay, so the unitary group, so this is the so-called unitary group of matrices, the corresponding unitary group of matrices. Is by definition, if you like, well, I just computed it, it's the set of U in GLNC, so that U dagger equals the identity. U dagger is equal to U. Okay? Okay? You know that. And somebody calculated that for you in some class. Right, maybe. And you didn't make the next step. I'm sure. The next step is to say, look very closely at this equation. Mathematics is the subject of equations. Right? This equation, U times U bar transpose, is some nonlinear equation. Right? There are many nonlinear equations there. You know, the identity has many zeros in it. Right? So, for example, first row times first column equals 1, but there's a bar trans, I don't know. You see what I mean? You have to multiply by bar transpose. So, yeah? Okay, first row, second column is 0. Yeah? You're looking at a huge number of equations here which are nonlinear. Right? The second degree because it's just that times that. But with some bar, this is very, very complicated nonlinear phenomenon. This is nonlinear. So, mathematicians, and now I remember very well my first lecture when I was more or less your age from a wonderful professor as I was a graduate student. He introduced me to the linearization of this problem. Of this, let's call it the setup. You take linear algebra 1, linear algebra 2, you take linear functional analysis 1, you take linear functional analysis 2, right? Hahn-Banach theorem, Yeah, closed graph theorem, all these various definitions of linear, these are mathematics stuff. Every physicist and every applied scientist knows that nothing is linear. Yeah? Essentially, nothing is linear. You linearize highly nonlinear things to simplify them to get some idealistic solution. What might be going on in the world, right? It is almost alchemy. It is an artistic work to know how to linearize natural phenomena into mathematics in a linear setting. Yeah? This is not talked about enough in mathematics. Some mathematician goes through and says, I do nonlinear mathematics. And I tell him, all of mathematics is nonlinear. Yes. So what? But it's a big problem directly attacking nonlinear phenomena. Let me give you an example, the Korteweg-de Vries equation. So if you have a wave, for example, in a plasma, this is called the Kadantsev-Peterswili equation. Is anybody here from Georgia? This is called the KP equation. If you have some sort of plasma and it's moving, and there are waves created. The simple model of this is called the Korteweg-de Vries equation of very low-level water waves. And the differential equation which models this, low level means what do you call shallow. The differential equation which models this is nonlinear. And the phenomenon that arises from that simple differential equation is incredibly beautiful and incredibly complicated. Right. Linear mathematics is, in reality, boring. So, I start with a nonlinear situation of the unitary transformations that I want to linearize. Now remember, my professor told me, here's how you do it. He said, what you want to do is consider curves every physicist has seen these letters. You want to consider curves. T is a parameter. Okay, T is a real number. You want to consider curves of operators. This is already something, right? Some guy says we have a curve in this room. I say, no, you have a curve of operators. Well, I would hope this is unitary. So I'm interested in considering curves in the unitary group. Curves in the unitary group which look like e to the something t. Now this is pretty well motivated. Let me remind you how to think about this. You see this unitary group? This unitary group is U1. Do you agree with me? These are the one-by-one matrices. Well, shall I write it down and get you excited about a one-by-one matrix? No. We have to understand a one-by-one matrix. And then 2x2. Okay? So this one-by-one matrix is a number. That's U, a number A. And U bar transpose is A bar. And U times U bar transpose is A times A bar. And A times A bar, that has to be the identity. And that says absolute A squared equals 1. So U1 is the group of rotations. And you learn, it's non-trivial, but you learn that if you have a group of rotations, that you should really think of the group of rotations as e to the it. Here the Hamiltonian h is just the number 1. Right? You learn that. And you know very well that's highly non-trivial. Because behind all of this, you find the definition of pi. Yeah? You find basic phenomena all over the place, just in U1. Okay? I guarantee it. If you start thinking about U1, you'll realize it's interesting. Okay? So this is a very good model. In this case, this is very high dimensional, but this is just an operator. It's just not a number. It's very high. So the question is, what is the condition on H so that UT is unitary. So in other words, you're interested, now in the language I will use from now on, in finding one parameter subgroups of the unitary group. These are subgroups, watch this. These are subgroups. The subgroup condition is, watch it very slowly. Tell me when I'm making a mistake, I always make terrible mistakes. E to the I, T, H, that's one group element. E to the I, S, H, and I say, oh, ha, 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 that's E to the I, S plus, oh no, I'm doing it in the right order. T, S of H. Is anybody going to complain? You shouldn't complain, because these things here commute. You understand? If you look at e to the a times e to the b, and if you're crazy enough to think e to the a times e to the b is equal to e to the a plus b, then you really believe that every operator commutes with every other operator, right? Right? You have a power series for e to the a. Oh, this is a power series, right? I mean, the usual power series. Okay? Maybe I should write that. But you have a power series in e to the a, power series defines e to the b. You multiply those things together. To get that thing to e to the a plus b, you have to mix terms all the time. And it won't work unless they commute. But these things commute, obviously. H commutes with itself. So this, you see, is a group action. E to the t, e to the s, e to the t plus s. It's called a one-parameter group. I got so excited when I saw this the first time in my Mathematics Live. It almost turned me on to mathematics. I was very lazy still. But my God, you have an operator and you take e to that operator. I couldn't believe it, man. You take an e to an operator. How about log? Well, why not? You do an operator, log of an operator. Anything of an operator, sine of an operator. Physicists do anything, man. I mean, no, it's good. It's good. It's really good. Physicist said, hey, this is natural. You know, for some physical reason, it's natural. So he takes some incredible thing, mathematician. My God, how'd you do that? It just doesn't make any sense. And then you look into that and you say, hey, e to an operator. Well, just let me think about it. E to an operator is equal to this, right? Right? Okay? You don't mind, do you? Okay. What does the mathematician have? The physicist doesn't care, it works perfect. But a mathematician wants to check something. What's he want to check? Convergence, yeah. I mean, if this thing doesn't converge, then you better think about how to make it converge. No, really, because it should make sense. If it doesn't converge, there's something wrong. We have to figure out how to make it converge. This converges uniformly on any bounded set you find. It's converges really uniformly. It couldn't be a better convergence to hope for. Okay, you can just check. Is okay. Okay. Okay, let me get back to my thing. I say this group here is really highly non-trivial. I don't understand it, so I had some idea from classical mathematics of looking at curves, and these curves are one-parameter subgroups. Okay, and again, what is the condition on H? So that UT is unitary. A curve in the unitary group. when you're doing mathematics, we were talking, you work well with formulas, but you don't know what to do sometimes in terms of conceptual thing. I guarantee you the first thing to do is just write down some definition. Okay? So the thing is, what we want to check somehow or another that this thing is really unitary. I have found in my life with students that they say, I don't know what to do. I don't know what to do, Professor. Tell me what to do. No, I'm serious. I'm not, I like it. So, yeah, but you can imagine what am I doing here? It's like a 2-year-old kid. Tell me what to do. Yeah? Then I often ask, what is the definition of unitary? Really? Right at the beginning. Sometimes I'm even critical of myself. I'm there calculating, and I ask them, what the hell are you calculating? You don't even know what you're calculating. What is the definition of unitary? Really check it. So what we want to check is this, right? Right? And then, okay, check. Yeah. Well, I don't know, I had to put this in here. Right? Oh, yeah.
How did you come back to this? Why did you verify like the dagger thing?
Oh, he's making a very good point. I'm actually, thank you for this point. I introduced the exponential map at the level of matrices. As you know, I can just, it's at the level of operators, it's the same. Okay? So, I could be doing this with an abstract inner product or just with the standard 1 and Cn. So it doesn't matter, it's absolutely the same. Okay? Let's leave it a little bit abstract for a moment, but think what you want, okay? Okay? Now, here comes an idea. I don't know whether you would have this idea or not, but it's a good idea that somebody has. That's if and only if, right? A curve is 0, fixes a point. If it's, you see, this curve doesn't move. Right? There's no velocity to this curve. It means it fixes everything. That's the statement that the velocity vector is always 0. You have to have that idea. Okay? This condition is the same as the curve has a velocity vector, but it's always 0. Right? Let's compute it. This thing is a product. If you like, think of it in your situation there, okay? It's a product, but it doesn't matter. It's a bilinear form. So it's the differential of the first thing times the second. Say let's differentiate at t equals 0. It's the derivative of the first thing times the second plus the derivative of the second times the first. So this is the derivative of the first thing times the second plus the first thing times the derivative, the first thing at 0 times the derivative of the second.
Where did the e to the I t will be?
At the equal 0.
I evaluated it at 0.
Oh,
Okay? It's the product rule. You have to look what a bilinear form is, but it's just the product rule. Derivative of the first times the second plus the derivative of the second times the first. But I'm evaluating at t equals 0. That's enough to check that at t equals 0 for every point. Okay? It's just amazing, and you can see why the notation here, using I here, is more than just for fun. Because what is this thing in the first argument? It is antilinear, right? So that says this is equal to 0, right? So that's constant. And this I comes out as, I'm going to cancel the I, so it's minus. And this I here comes out as plus, so I just get that. Okay, you see the calculation? Just write down the definition. definition of unitary. Differentiate, evaluate is 0. That's equivalent to the thing being true everywhere. This is true for all x and y. Well, let me write it this way. Hx, y equals y. Now, let's get back to Mihai's that your name, right? Mihai says, why don't you do it in the matrix language? It's okay.
No,
But-
because I saw this, I saw this before you did all the derivatives, and so just by plugging in the dagger.
Just by plugging in the dagger and differentiating there.
Hmm.
Yeah, you can do the same thing here. Yeah? Okay? So, actually, I want to leave it at the abstract level for a moment, if you don't mind. I'll come back to this, okay? You know that formally speaking, if you have an operator, by definition, the adjoint operator is defined in this way. That's how you define the adjoint operator. Okay, that's the definition of the adjoint operator. And it says that then U of t is unitary if and only if H is self-adjoint. Right? Because look, I push it over here and I didn't do anything. So that says the adjoint is just H itself. Okay? Now, Mihai did a calculation in his head here at the level of matrices. I could have done the same thing as self-adjoint at the level of matrices. Okay? So at the level of matrices, self-adjoint means H equals H dagger. The adjoint operator at the level of matrices is just bar transpose. Well, this is for any form, so you got it. Isn't that beautiful? We know that you get a curve, a one-parameter group, in the unitary group exactly by e to the iht, where h is a Hermitian operator. Hermitian operators linearize unitary operators, yeah.
Okay, so why do you need to differentiate at the level of matrices?
Hmm?
I mean, if you take e to the iht,
Yeah.
and you apply the dagger to it, it's
Yeah.
just e to the minus I h dagger t, because you conjugate everything.
Yes.
And then this product,
It kills you.
it has to give I.
I guess so. What he's saying, you don't have to do anything here.
We don't have to do anything.
Yeah, because you like numbers, so let's do this. So e to the I h t is u times e to the I h t transpose here. Yeah? No. Yeah, you just I know what you're doing. Ha!
It's very easy. I mean,
Huh? I know what you're doing.
it's like obvious.
Yeah, yeah. And now you say, okay, e to the I, this is equal to the e to the I h
minus epsilon.
Minus h dagger.
minus h dagger. Anybody know what Mihai used here?
I mean, you go to the series and then you go back. I mean,
Yeah, well, then you differentiate and you look first order terms, actually. So, you know what he used there? That h dagger could be used with h.
yes, I use it. I mean,
Yeah, how do you know that? How do you know that? I mean, some of these little trivial things like this, I don't know. I mean, maybe it's true. It's in fact true, probably. Is that clear? He used that though, in any case, right? But what his point is another way to prove this is put in the power series here, and the power series must identically, and compare to the right-hand side, so every coefficient of the power series must vanish, in particular the linear coefficient, and that's what you say is there, and you're right. Okay?
It has to be normal so that you can.
Hmm?
It has to have a property. I mean, it has to be normal so that you can.
What do you mean normal?
matrix needs to be
Normal
normal.
operator.
I don't know about normal, what is it, he used some word, I know what you mean by normal, what has to be normal?
H has to be
Why?
normal, so then they commute.
H bar transpose and H commutes if it's normal.
Yes.
Well, why is it normal?
That's the definition of normal. They define it like this.
No. I took this, come on, give me a break. I take this operator H. I look at e to the I(t). I want this thing to be unitary. And he said his little argument here works if H is normal. But I don't know what H is. It's perhaps non-normal. I'm completely no normal guy, you know? Okay. So, I mean, he used something, and I'm sure you can make all these arguments precise, particularly the power series argument is completely precise. You see, he just put in the power series and a check what had to happen. I mean, at the level of matrices, I think that's a great argument. Okay. Well, what about these operators? There was one thing we learned last week, or yesterday even, talking about it in more detail, is that diagonalizability is a fundamental concept. So let's check about diagonalizability of these operators. And that will be my last remark. Let's have some fun. Let's take a U in the unitary group. We know only one theorem. This has an invariant state. This is a general theorem about any operator. It has an eigenvector. Right? That's the best we can say. Okay, let's call it U1. Okay, let's look at the vector space, and let's say this defines a one-dimensional. The state is V1. So, ha. Right? The operator stabilizes this line, therefore it stabilizes the orthogonal complement. Therefore I apply the same argument to the orthogonal complement, and I go again and tell God I don't need to go again because I know induction. Okay? So we decompose the vector space into lines, right? How did I get V2 from V1 in the orthogonal complement? How did I get V3? Okay, each step is orthogonal. Yes? I'm producing here an orthogonal frame, a unitary frame. This procedure produces a unitary frame. Wow. Okay. So, what is the statement? The proposition is there exists a unitary frame with, say, U1 through UN, so that U of UI is lambda I times ui, it's invariant frame. And what is with the eigenvalue? It's a one-dimensional, it's u1, right? So the eigenvalue, that thing is invariant, that state is invariant, so on, it's u1 on that state, it's the statement that the absolute value equals 1. It's a rotation on this stable frame. Okay? So the statement at the matrix level is it's the same statement. Every U in the unitary group of matrices can be conjugated U goes to, let's say, K, U, K inverse for some appropriate K in the unitary group to a diagonal unitary operator. So unitary operators are really a lot better than general linear operators. Every unitary operator can be diagonalized, and not just for fun. You can diagonalize it by conjugating with a unitary operator. Okay? Then that's very, very nice. Let me close by the analogous discussion of the Hermitian operator. What is the analogous statement with Hermitian operators? Okay? Okay, let's see what happens. Suppose x, this line, we know we get it for free, equals L, say V1, is H invariant. That means that H applied to X is an eigen, is lambda times X. Well, let's see what that means. Suppose X is perpendicular to Y. X can be written as lambda, well, I take a non-zero eigenvalue, otherwise this is silly. So, lambda to the minus 1 lambda of xy. This is minus 1 h of x y. This is lambda minus 1 x h of y. X perpendicular to y, or y perpendicular to x, says that h of y is perpendicular to x. This says h stabilizes the orthogonal complement. Isn't it terrific? I start with something, Hermitian operator, God only knows what it's doing on this line, has some eigenvalue, and it stabilizes the orthogonal complement. This says that H has an invariant unitary frame.
So you choose.
I have, so what? I still have I have the,
No, but if
it is real, but,
if lambda is not real, it doesn't go in as lambda, and that goes in as
Oh, thank
you.
well, let me organize this. Thank you. Okay, thank you. Because it comes out as bar, that's his point, it comes out as bar. Yeah? Okay, so this is the invariant unitary frame, that's great. That says that in this frame, H of, well, let's write it as, of ui equals lambda I ui. And now, what is lambda I? This is we're going to look at what's lambda I looking like. Let's see what happens. Let's say, okay, H of ui is equal to lambda bar, that's his remark. Ui. This is equal to ui, okay, it's lambda I. This is equal to ui h of ui is equal to ui lambda I ui is equal to lambda I ui. Sorry to bore you. All right? So here it comes out as a bar, that was his remark. But since H is self-adjoint, yeah, I push it over here and it doesn't come out as bar anymore, it comes out as lambda. So this is a statement that lambda is equal to lambda bar. And this says, so where the lambda i's, so this is a little calculation here, where the lambda i's are real numbers. We talk about the symmetries of the geometry. You linearize the problem. The eigenvalues of the linearized problem are real numbers. Now, if you have a good Hermitian operator, which is positive definite, they are positive real numbers. And these positive real numbers can start having meaning in terms of probabilities, for example. So, we're coming very close to discussing quantum mechanical things. Anyway, I promise you all, this is just an introduction to the mathematics of the subject. You're responsible for the physics. Okay. We do have now a very interesting class of operators, namely the Hermitian operators and the back and forth discussion between Hermitian and unitary operators by the exponential map. Okay? So that's the end of my linear algebra.